Hello and welcome to From Data to Decisions. I'm Chris Mack, the instructor for this class, and this is lecture 23, where I'll look at how to calculate and use leverage and influence when looking at regression results. We'll do this in Excel and in R. I think R is going to prove to be the more useful tool, although for a single explanatory variable, we can do everything we need to do in Excel as well. So let's do Excel first. I'll go through it quickly. Begin by doing a linest. Here I've got the set of data, which is a calibration of a flow meter. This particular experiment, and here's the reference up here, the paper the data was taken from. We have a flow meter that's measuring the amount of liquid nitrogen flowing through a system. We want to calibrate that flow meter and understand its systematic errors. So they pumped liquid nitrogen through the system. The flow meter measured how much was flowing through, and then they dumped it into a container and they weighed it, and they looked at the difference between what the flow meter said and what the weight was that they actually measured. So this is essentially the error in the flow meter as a percentage on the y-axis. And then they did an experiment through temperature. So they varied the nitrogen temperature and saw a systematic error as a function of nitrogen temperature. So that's the experiment. And they were wondering, does a straight line model work to create, say, a temperature calibration that we could use to offset flow meter values? Well, they fit a straight line, and it's a reasonable fit. The R squared is 0.93583. And here's the linest results with the slope and the intercept. Well, now we want to do some diagnostics on the residuals. So in the next tab, we show how we're going to calculate the externally studentized residuals, because that's where we need to do all of our diagnostics. To do that, we first have to get the leverage. The leverage is HII, the diagonal of the hat matrix. For a single explanatory variable, we have a simple formula right here that allows us to calculate it. You see it has a minimum leverage of 1 over n, and then the leverage can be greater than that depending upon how far away the x value of the data point is from the mean x value. So we plug that formula in, and I have this column of data here. Next, I'm going to normalize that, divide the leverage by its average value. The average value is P over N, where P is the number of the parameters in the model, in this case 2. So I take the leverage, multiply by N, divide by P, I have a normalized value, 1 equals the average. And we're going to use that for some plotting. I can also calculate the internally studentized residual, and here's the formula for the internally studentized residual. It requires me taking the residual and divided by the standard deviation of the residuals and the square root of 1 minus this leverage. So the standard deviation of the residuals come from our linest. It's right here. CY it's called. It's also the standard error of the y values. If you want to calculate that by hand, you have to be a little bit careful. Using an Excel standard deviation function, we need to make sure that we divide by n minus p in this calculation, not n minus 1, not n minus p. So I have to make some adjustments here to standard deviation.s in Excel, which uses n minus 1. So make sure you don't make that mistake if you're trying to calculate the standard deviation, standard error of the residuals from the residual data itself. That gives us the ISR. We can calculate the ESR. I've pasted the formula for ESR from the class notes into the spreadsheet so you can see it. The spreadsheet, by the way, will also be available on the class website for you to download and play around with yourself. The absolute value of the ESR we'll use for graphing. We can also calculate the Cook's distance, again using the formula from the notes. You see that it's related to the ISR squared and the leverage. And finally, the DFFITS is related to the ESR as well. DF beta is a little bit harder to calculate. I'm going to leave that out of Excel and do it strictly in R. Well, once we have columns of all of these things, we could ask, well, what's the biggest ESR? What's the biggest Cook's distance? Maybe I'll copy this formula over here to the ESR and see that the largest ESR is 3.47. I can also calculate the critical Grubbs t-value. I have to remember to use the degrees of freedom of n minus p minus 1, not just n minus 2, like we did where we were only dealing with data around a mean. But again, for a reasonable value of n, that's a small difference, unless p gets large. But nonetheless, that's our critical Grubbs value. You can see that our maximum residual is only slightly above that. And this is for, what did I use? 95? Yeah, 0.01. That's what I used. 99% confidence interval, 0.01 probability. And so this is just barely large. But we might want to check, is it a high leverage data point? And is that going to be a problem because of it? Well, we can look at the Williams graph to help us understand that. Right? So here's the Williams graph. That's the maximum value right here, and we see its leverage is very low. The minimum leverage is 1 over n, and normalized by the average, minimum leverage is 1 over p, which in this case is 0.5. Can't get leverage smaller than that, and this data point has pretty close to the smallest leverage. Our high leverage points, low residuals, as of course you expect to have happen. We can also look at the Cook's distance, and this is the same data point. It has the high ESR, has the largest Cook's distance. The 4 over n cutoff is about 0.11, but we also like to compare the Cook's distance to about 0.5 to 1. How many standard errors away from the original fit would a new fit be if you took away this one data point? And you see we're a long ways away from 1 and just barely above that 4 over n kind of guideline. It's not a cutoff, it's not a statistical test, just a guideline. So that when it all comes down to it, we look at all this data, this kind of extreme residual probably not going to hurt us enough to worry about. Well, that's how we perform these kinds of tests in Excel. Let's do all the same thing in R, and I think you'll see that R is a little bit easier to do. Here's the same data. I have converted it to a CSV file from Excel, and I've read it in. I will read it in right now. And if I double click on the flow and the global environments, I can actually look at the data, and I see its temperature and a variable called flow.difference, and we have 39 data points. We can go look at any of those values. So our normal routine is going to be begin by plotting the data. So there's our plot. Then we're going to use the LM function, linear modeling function, to model this data. This is our ordinary least squares regression. The way we're setting it up, we'll have flow.difference as the y value as a function of this tittle. That means as a function of the flow temperature. So we ran that model. It generated a model object. I named model, a linear model object. And if I look at the summary, see all the statistics, the coefficients, standard errors, etc. And it all matches LinEst perfectly. We're going to do testing on the ESR, so the first thing we have to do is extract the externally studentized residuals from the model. And there's a library called MASS, M-A-S-S. Apps has that, so I'll install that library and generate those ESRs. So now I've got 39 ESR values, a few of them listed. Well, the next step is generally to plot those ESRs. So here I'll plot the ESRs, externally studentized residuals, and I plotted them versus the fitted values. That's the normal way to do that. And again, we see just like the graphs we saw in Excel. Potential problem point here that we worry about. Often it's useful to plot the absolute value of the ESR. So you see what I did up here. Instead of saying plot ESR versus fitted of the model. Right, so the fitted of the model gives me all the fitted points by hat values. I'm going to plot the absolute value of the ESR. So it's that simple. Change a graph from ESR to the absolute value of the ESR. Now we want to look at leverage. The way we look at leverage is using the hat values. And I can extract all the hat values from the model with this function called hat values. So if I run that, you see down here in the console, it just dumps the 39 diagonals of the hat matrix. Use. Well, one way for us to use them is to create a Williams graph. So I'm going to define a variable called norm underscore leverage, which is simply the normalized leverage. So I'll take the hat values. So here's my hat value function. And I'll multiply by n, which is simply the length of the ESR array. So this function length tells me how many data points are in the vector ESR. And that, in this case, is 39. Divide by 2 because I have 2 parameters. And that gives me the normalized leverage. And now, if I run that and then plot it, I have a Williams graph. Magnitude of the ESR versus the normalized leverage. Here I have the 2 points of 2.0, which I consider the high leverage points. I have the points that are the large ESR, but they're very low leverage. This generic plot function has some plots specific to a linear regression model. So if I tell it plot the model, it has 5 built-in graphs that we can use just by saying which equals 1 through 5. So if I do 1, a plot of the residuals versus the fitted values. If I do which equals 2, it gives me the QQ plot. We haven't talked about a scale location plot, but what I want to look at is the Cook's distance, 4. If I plot 4, I get a Cook's distance graph. This shows me the Cook's distance versus observation number, and it labels the 3 biggest points. And this is the Cook distance, largest point. Well, I can do that myself if I wanted to, because there's a function called cooks.distance. So I take the function cooks.distance and give it the model, and it will dump all the Cook's distance values into the array D. So here they are, D, 39 values, and see the values in that array. And I can do things like plot them myself. So I can plot them, for example, I might plot them versus temperature if I so desired. That's what this plot shows. Here's the Cook's distance versus temperature for all the data points in the data set. There's the biggest one, of course, as we've seen before. I can plot it versus the fitted flow difference, y hat. And I can investigate the magnitude of the max. So I could say, for example, I might type in max of D. And I run that, and it gives me the max value of 0.137. And I can compare the max value to some criterion that I use for judging whether a data point's highly influential. All right, last thing, we talked about DFFITS. Well, there's a function called DFFITS. And if I run that function, giving it the model, the object of the LM function, it gives me all the DFFITS for each data point. Well, I might want to know what's the biggest one. So I can take the max of the absolute value DFFITS, because I don't really care if it's making the y hat bigger or smaller. I just want to know how much it's changing. And if I run that function and display the biggest, I see that the biggest is about 0.6 right here. 0.6 standard errors away is how much the predicted y value changes with or without that particular data point. And it comes from the same data point we've been looking at. When it starts getting close to 1, I start worrying. 0.6 is borderline, probably not enough for me to worry about. Again, if it gets close to 1, that means it's the effect of that one data point is approaching the standard error in my predicted value. I might be more interested in how data points affect the parameters of the model. So if I run DFBETA of the model, I get an array of all the DFBETA values for every data point for both the intercept and the slope. And then I can ask, well, what's the biggest one? So the max of the absolute value of the DFBETA, this would be for both intercept and for the slope. I can ask what that is, and it turns out to be about 0.3. So that's the biggest. 0.3 standard errors is the biggest change in either parameter, intercept or slope, given the removal of one data point, which I'm going to tell you it's going to be this data point, as we've seen before. Well, 0.3 standard errors is probably not big enough for me to say I should do something about this influential point. As we said in the lectures, if we had our druthers, we might go and collect some more data at this particular temperature. But just given this data set, I think we don't have much to worry about. Well, that's how we use R to do influence analysis in our regression. Thanks for listening.